Hello, everyone, and welcome back. My name is Mr. Kovalt, and in this video, I'm going to be going over what is potential energy. So let's get into this. So before we get into potential energy, let's remind ourselves what the law of conservation of energy says. So the law of conservation of energies tells us that energy can neither be created nor destroyed, but it can be transferred from one system to another or transformed into one form or another. So we don't lose energy, we don't gain energy. It's just transferred, transformed to one form or another. So now that we got that out of the way, let's keep that in the back of our mind when we talk about potential energy. So potential energy is the retrievable, stored form of energy of an object that an object possesses by virtue of its position or its state. So I'm going to go over an example of this in just a moment. So let's talk about a coin flip at a football game. So you flip the coin, right? So I have a coin. Okay. All right, here's my coin. I got a penny. It's not typically what is used when you flip a coin at a game, but so be it. That's all I have. So you flip a coin, right? We flip the coin and it goes up and down. Let's do that again. Flip the coin up and down. So what's happening during the process of flipping the coin? So where is this energy coming from? So it's on my thumb. So my thumb has energy, like there's stored chemical energy in my muscles. When I contract my thumb, I flip the penny upwards. The energy of motion, I put motion into my thumb, right? This goes back to kinetic energy. Remember, kinetic energy is the energy of doing work due to the motion of an object, right? So my thumb moves. As it's moving, it pushes the penny against gravity, right? So it's forcing the penny to move now. So it's transferring energy to the penny. The penny then has kinetic energy because it's in motion. But as the penny travels up to its highest height, it's going to stop and rest just momentarily. At that point, there's no kinetic energy because there's no motion, right? So then the question is, where did that energy go? It can't just be destroyed and disappear. It's got to be transferred or transformed into another form. Now, part of that kinetic energy as it's traveling through the air is then being transferred to the air molecules because it's bumping up against the air molecules. It's colliding with those air molecules, therefore transferring some energy to those molecules, to the particles, and giving them more kinetic energy. So there's some transferring of energy that way. But also, you have an increase in what is potential energy. So as it goes up, it's moving away from the ground, right? So it's getting higher from the ground or from my thumb, right? But either way, it's moving, its position is changing, it's moving further from the ground or earth, and it stops. So remember, potential energy is the retrievable, stored form of energy an object possesses by virtue of its position or state. So, position. So, the penny's position changes with regard to the ground or the earth, right? So, as it gets further from the earth, it is gaining more potential energy because the height potential energy is related to the height or distance from the earth, or in this case we're talking about gravitational potential energy. So just like I did before, I'll write down the formula for gravitational potential energy. So for gravitational potential energy, the formula would be equal to the mass times gravity. So mass times force gravity times height. So height is involved. So the higher you get, the more potential energy you have. So since you only have a certain amount of kinetic energy, once all of that kinetic energy is converted to potential energy, then you only reach a certain height. You can't get higher than that because that means you would have to get more energy from somewhere else, right? So once all of the kinetic energy is transformed into potential energy, it's going to stop, right? So no more kinetic energy. And then now all of that kinetic energy is converted to potential energy. So no more potential energy, no more energy is being added to increase potential energy. So it's going to stop there. And then what happens? Again, this is retrievable stored energy. So the energy there is stored in the penny due to the height that it is from the ground. So also you have the force of gravity acting on this. It's going to then start to come back down. It's going to gain motion. As it gains motion, that potential energy is being transferred into kinetic energy, thus increasing the motion. So as it decreases and moves towards the ground, it's going to that potential energy is now being lost, right? So high potential energy as it travels closer to the ground, lower potential energy. Well, where is that potential energy going? It's going into the speed the of the coin. So as it gets closer to the ground, it's going to move faster and faster until then it hits the ground, right? And in that case, the kinetic energy of the penny goes into the work of bending the blades of grass. So it hits the grass, that's going to move the grass blades, it's going to bend the grass blades. And so that kinetic energy is doing work on the grass. It's moving the grass, bending the grass. And so, excuse me. So here I have a picture. So here is low potential energy. I flipped the coin with my thumb. I put energy into it. Now it's got kinetic energy here. As it travels higher, that kinetic energy is being transformed into potential energy. It stops up here. Now all of that kinetic energy has been transferred or transformed into kinetic energy. But then, I'm sorry, into potential energy. That's retrievable stored energy. And then that energy, that potential energy is then converted into kinetic energy again. So we're taking that potential energy that's stored and we're transforming it back into kinetic energy as it falls to the ground. And so that is an example of how the kinetic energy and the potential energy in your coin gets transferred during the process of a coin flip. And again, of course, how that kinetic energy is then used to do work on the grass once it hits the grass and causes the blades of grass to move. Okay, so there are different kinds of potential energy, right? So as I mentioned here, there's gravitational potential energy. That's the potential energy due to gravity, right? So the closer you are to the Earth, the more that gravity is working on you, right? Um, the farther you get from the Earth, so I flipped that around. Sorry. So the farther you get from the Earth, the more potential energy you have. The closer you get to the Earth, less potential energy. So due to the position of the coin or the object, the potential energy is either going to be higher or lower, right? So we also have alkaline batteries. There's potential energy in the alkaline battery. That potential energy can then be transformed into kinetic energy in, say, the form of making an electric car move, right? You put the batteries in the car, it causes that chemical potential energy in the alkaline battery then gets transformed into kinetic energy in the toy car. Your plate of pasta that has some chemical potential energy in the bonds of the molecules that make up the food you're eating, that those molecules, those bonds can then be broken, that energy is released, and then that can be transformed into, again, different kinds of energy, heat energy, uh, kinetic energy in the form of contracting your muscles and moving your arms, your limbs, things like that. So that way you can go on a marathon run, right? So you load up on the carbohydrates, and then that potential energy in the molecules can be converted into kinetic energy during your marathon. So this is a couple of examples, a few examples of different kinds of potential energy. So the next thing we want to talk about is the relationship between potential energy and stability. So we're going to talk about that next because that's going to be important in understanding how potential energy is related to, say, the bonds or that hold atoms together in molecules in chemistry. So let's talk about that. So next is potential energy in relation to the stability. Okay, so let's talk about potential energy and stability. So let's understand that a system's stability is a measurement of its tendency to change. So the more stable a system is, then it's less likely to change, right? Because it's stable, it's not going to want to change from that stable position, a stable state. So less stable systems want to achieve stability, so they're going to move in a direction that's going to give them more stability. So they're more likely to change. So if we understand stability is in terms of a measure of its tendency to change, then more stable is less likely to change, less stable is more likely to change. And so the key thing that we want to understand is in terms of a system stability, likely to change, and its energy, anytime a system shifts from a more stable state to a less stable state, the potential energy is of that system increases, meaning that its likelihood to do work on something is higher, right? Remember, energy is the capacity to do work. So if there's a higher potential energy, then there's a higher capacity of that system to do work. And so, if we're in terms of stability, if we move from a more stable state, it's less likely to change and therefore cause change in something else or to do work. If it goes from that more stable state to a less stable state, that means more potential energy is there. It absorbed energy from somewhere. So energy is being absorbed to increase that potential energy and therefore increase the instability or lower the stability of the system. So it's more likely to do work on something in order to reach back to stability. So if we look at my coin toss again, right? So I have my thumb here. I'm going to flip the coin. So here at rest, it's stable. It's in my hand, right? It's on my thumb or in my hand. And so as it's resting on my hand, it's stable and therefore less likely to change, less likely to do work. So as soon as I put energy into it, I flip the coin, I've added energy to this system. Now the coin goes up. And so it's got kinetic energy, it's going to go to here. So now it's in a state here where it's at rest momentarily. So here versus here, when it was in my hand, it was stable, lower potential energy, less likely to do work. Now that it's up here, it's unstable. It's got a higher potential energy. It's more likely to do work, right? It has a greater capacity to do work, higher potential energy. And so when it falls back down, it's going to gain kinetic energy. It's going to be bumping into air molecules, pushing them, adding energy to those molecules, doing work on the molecules, right? As it's falling down to the ground. When it hits the ground, it's doing work on the grass blades, right? So lots of potential to do work, and then it does work on the molecules and the grass blades. So here, less stable, greater capacity to do work, has a higher potential energy. Here, when it's in my hand, uh, more stable, it's less capacity to work, has a lower potential energy. So there's a commonality here. There's a common feature here when we're talking about systems gaining more energy, more potential energy. And so here I have it written down, more stable. If it's more stable and it gains more energy, it absorbs energy, that's going to make it less stable. If you have a lesser capacity to do work and you gain energy, that means you're going to have a greater potential to do work. If you have a lower potential energy and then you gain energy, like the flipping of the coin, right? I added energy to the coin, then you're going to have a higher potential energy um, as well. And then the coin in the hand, again, my example, coin in the hand, I add energy to that coin by flipping it. Now the coin's in the air. It's going to have a greater potential energy, greater capacity to do work, and so on. So now that we've kind of um, talked about the relationship between potential energy and stability and the ability to do work, capacity to do work, let's now apply this to molecules. Okay, let's talk about the potential energy and stability again with respect to atoms and molecules. So, as we said before, the potential energy and stability, the less stable something is, the more potential energy it is, and there's an absorption of energy involved. So here, energy is also needed to separate two atoms held together. So you need to put energy in, energy needs to be absorbed in order to separate those two atoms away from each other. So when they have this attractive this mutual attraction to each other that forms a chemical bond. So you need to overcome that bond, and in order to overcome that bond, you need to add energy. So here we have a stable state where the atoms are bonded together, they're close to each other. So again, potential energy is related to positioning. So the attractive particles, the atoms that are attracted to each other, are held together. And so if we add energy, we can pull them away from each other and thus increase the distance from each other, increasing potential energy. Because again, they're still attracted to each other, so they're going to want to come back together. So there's an increase in potential energy as you pull them apart. Okay, so that is what is happening in the adding of energy to break a bond, right? So you've got a stable molecule, and so it's got a low potential energy. You put energy in, you're going to pull them away from each other, increasing the potential energy and thus increasing the capacity to do work. And I'll talk about that in a moment. So the energy supplied is increases the potential energy of the less stable separated atoms, right? So again, remember, less stable means higher potential energy. More potential energy means more capacity to do work. And they'll do that work in order to come back to a stable state or a more stable state. So the potential energy of the less stable separated atoms, the energy is supplied to increase the potential energy of the less stable separate atoms compared to the more stable atoms that are bonded together. So here's some ways of stating this, right? So greater force of attraction, meaning they're closer together, right? You have a greater force of attraction when they're closer together. When you add energy to that, you are moving them apart, and therefore they're going to have a lesser force of attraction, right? So the farther you bring them apart, they're going to have a lesser force of attraction. Um, More stable, right? So more stable together, add energy, they're going to become less stable. They're going to have a lower potential energy when they're together, bonded together. Add energy, they're going to have a higher potential energy separated. And again, atoms bonded together plus energy leads to separated atoms that have a higher potential energy, a larger capacity to do work. Remember, energy is the capacity to work. So potential energy, higher potential energy means that you have a higher capacity to do work due to the change in position or state. So here I have a picture where I have the two, let's say, oxygen atoms. So here I have two oxygen atoms. This is part of the process of forming ozone, is to break the oxygen atoms apart in oxygen so that they can combine with other oxygen molecules forming ozone, which is O3, right? So the first step is you need to break the bond. You need to pull these atoms and separate them from each other. That requires energy, and that energy comes from the sun in the form of UV light. So the radiation from the sun will break the bond. That's the energy being added. That's going to separate the atoms, and then now that they're separated, they have a higher potential energy. They're less stable, so now they're able to do work. So the attractive forces are going to force them to come together again, or be come together with another oxygen molecule. So during the process of coming back together, they can do work. They can collide with other molecules. They can cause them to move, do more work, give them more energy, things like that. So in this process, we've talked a lot about energy being absorbed. When we're talking about changes that are absorbing energy, where energy is absorbed, those changes are called endergonic. Sorry, that should be a D. So that should be endergonic or endogonic, or it's also referred to as endothermic. So any type of reaction or change in a system that absorbs energy, that's going to be an endergonic or endogonic change or reaction or process. It's also referred to as endothermic process as well. Okay, well, what about changes that are giving off energy? Let's talk about those next. Okay, let's finish up by talking about reactions or processes where energy is released. So when objects shift, before we're talking about objects or systems shifting from more stable states to less stable states and how energy is absorbed when it happens. Here we're talking about when objects or systems shift from a less stable state to more stable state, right? So decreasing potential energy, that means that the energy is released. So, for example, a coin falling to the ground. When I flip my coin, it increases in potential energy, comes to a stop here at its highest height, and then it starts to fall back. That potential energy is being converted into kinetic energy along the way. So, that is a shift from less stable, high potential energy to a more stable towards the ground. So less potential energy as you go down. So becoming more stable. Atoms coming back together to form a bond. So you had the less stable state of the atoms being separated. When they come closer together, the potential energy between them is decreasing. They're losing energy and they come back together and they're more stable. So there's a loss of energy there. Energy is being released to form the bond. So these types of changes that release energy are called exergonic or exogonic or exothermic changes or reactions or processes. And so going back to endothermic or endergonic or endogonic, endo you could think of as into, going into, like entrance. Endogonic, energy is going into or being absorbed by this system, right? Here, exo, think of exit, exiting, going out. So energy is being released, it's going out from the system. So that hopefully is a way that you can remember the difference between exogonic or exergonic versus endogonic or endergonic. or exothermic, endothermic. Okay, so now let's look at a few of these sorts of examples here. So lesser force of attraction, meaning the atoms, for example, are spread farther apart, or the marker here or the object is moving away from the Earth. So the farther you get from the Earth, the less attractive force you feel. So lesser force of attraction will lead to a greater force of attraction and release of energy. So when the atoms come together, release of energy, you're going to feel a greater force of attraction. As the object falls towards the earth, it feels a greater force of attraction. So losing potential energy, it's releasing that energy in the form of, say, kinetic energy if it's falling to the ground. Less stable is going to become more stable by releasing energy. Remember, less stable means higher potential energy. If you become more stable, you lose some of that potential energy and it's released in the form of some other form of energy like kinetic energy or heat energy or something like that. Higher potential energy, as I said, will go to a lower potential energy, losing your potential energy, so you're releasing energy. Separated atoms have a higher potential energy. They come back together, they bond, lower potential energy, so energy is released. And then, so finally, I want to finish up with what is called an energy diagram for reactions. So there can be a difference in the potential energy between reactants and products. So when the reactants come together and form products, the products could have a higher potential energy or a lower potential energy. And so that just depends on the reaction. So in here, you have the reactants here have a lower potential energy, and then they react and they form a higher energy product. Well, if the product has a higher energy, that means that energy is absorbed. It goes into the reaction, into the system. Here we have reactants at a higher potential energy. Products end up in a lower potential energy. So here, to go from high to low, you're losing energy. So this would be an example of an endogonic or endothermic reaction. This would be an example of an exogonic or exothermic reaction where energy is released. So you can compare the potential energies of products and reactants and see what has more energy, what has less. So if the products have less energy, that means energy was released. If the products have more energy, then that means energy was absorbed. I hope this is helpful. If you found this video helpful in any way, please like the video, share the video, hit that like button. Also, make sure you subscribe to my channel. Hit that notification bell. When you do, make sure you click all so you can get notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. Also, if you have an idea of a video I could do for you, please let me know. I would love to do that for you. Thanks for joining me and have a great day.